Good afternoon, everybody. My name is Neil Schrody, and I'm here with the second installation of Evofound, or a re-recording of it, because the last time when we did this, the sound quality was very poor. Today, we're going to be reviewing Evofinder similarity scores, what those similarity scores are, how they're generated, and what they're going to do for the examiner in trying to identify matches within the database that exists. Now, with the Evofinder software, the first thing that we're going to be looking at is the system is going to generate a three-dimensional profile of samples that we put into the scanner and add into the database. And then we can take a sample and run it across a group of samples within the database to focus on patterns that are reproducible between samples and get a shot-to-shot reproducibility or an identification of that between these samples. And what we're going to look at is we're going to look at the defined areas of interest, like the striker mark or a land engraved area, traces like grooves, things of that nature. We're going to use these automated comparisons to try and come up with a similarity score, which will give us a representation to show what is a possible match within the database. Now, a similarity score is a calculated value on a scale of 0 to 1. It's a normalized value that shows a representation of what one feature looks like in comparison to the other as the computer evaluates this. And one thing to understand about this is a point-to-point comparison. So in the case of a face of a cartridge case, we only have one firing pin impression, one breech face impression, one ejector mark. But for bullets, when we have lands and grooves, we have multiple lands, multiple grooves, and multiple slippage marks that will allow us to potentially see different areas matched to each other. So we can take the first land and look at it compared to the first land on another sample, then the second, the third. So we're doing one point and comparing it to every other point possible within the search parameters. And that's how we're doing a point-to-point comparison. Now, what does this similarity score mean for us? If we look at the similarities generated by the system, what we're doing is we're taking two samples, one on the top, one on the bottom, as we see here on the screen. The top sample is our test sample to be compared to the sample beneath it, and can be compared not just to one, but to numerous samples within the database. And the similarity, or the algorithms, are going to look and say, okay, this is where I find alignment between the two or non-alignment between the two to generate this similarity value. Now, giving you an idea of what this is, the two samples that we're looking at here would generate a similarity score of about 0.578. And what does that mean to us? Well, not much when we're looking at just a number, but it does show us that there is some similarity between the two samples in examination. What we really want to get into here is what do these numbers represent and how can we use them? So if I have traces that are well marked, nice striations, good features to them, we're going to get higher similarity scores in general for any sample that's run. Equally, if we have samples that have poor traces or poor markings on them, the overall similarity scores are going to be not as good. Regardless of the number, that doesn't tell us of an actual match. In fact, the software doesn't tell us of a match. It just indicates the likelihood that there may be one. The question now is, how do we identify a possible match between two samples? Well, here we are looking at two well-marked samples for both the cartridge case face and for a land engraved area. And if we look at these two, what is going to constitute a match? Well, in some cases, if we have a high similarity score, we're going to find large regions of interest within the sample that's going to show us a nice repeatable striation or characteristic between the two samples, and that will generate a high similarity score. In ones that have a medium amount of marking comparatively, this will give us not as much strong correlation as we saw in the previous one, or strong areas of interest, but we still have areas that are usable for an examiner to identify a match between samples. And then in some cases we get low similarity scores, and we'll see that there's even fewer regions that give us that region of similarity, but we still have features that an examiner can use to compare between the samples. Now, if we take any of these similarity scores for the low marked sample, a well-marked sample, whatever it is, if we look at a similarity score, it only gives us one number, which really doesn't give us any information to use here. We have to understand how these similarity scores relate to samples within the database. If we were to take multiple samples from the same firearm and run a search against them to get these similarity scores, we're going to see a grouping of these samples in the general same range of similarity as long as the sample or the source of samples is going to be consistently marking well. If we look at a larger volume of them, we actually get a nice bell curve distribution of these, and we can see how it groups nicely into a distribution of known matched samples. Now, the other end of the spectrum is if we're looking at samples that are not from the same source. And if we run a similarity or a correlation against a sample against known non-matched samples, we're going to get a different distribution of similarity scores, and they're going to generally be lower than those of the ones that are from the same source. And typically they're grouped a little more tightly based on how the software does its work. Now, if we wanted to take a look at both of these side by side, we can see how we have a group on the left of the known non-matches and the group on the right of the known matched samples, and we see there's a difference in the distribution and similarity values. Now, if I have well-marking samples, the ranges on these curves may be different. They may go 0.3 to 0.5 for the known matches and 0.8 to 0.15 for the known non-match. But what we're looking for isn't the similarity value itself, but the difference between the two. Now, when we have one sample that we're running against the database, we typically only have one outlier as far as the known non-match distribution curve. So we don't have this nice two-curve characteristic we're looking at right here. Normally what we're going to get for a search result is going to look something more like this if we print out a histogram of the similarity values from the software. Now in this case, you can see we have our known non-match distribution on the left, and there's one sample on the right which is sort of an outlier. What does this outlier mean to us, and how do probabilities come into likelihood of it being a match to the sample under test? Well, for those of you that like all of the fun stuff and wanted to check into the probability, you can look at the probability equation saying that the probability of a sample being a non-match to the non-distribution or the distribution of non-matched samples is a function of f of x from 0 to 1. Now, we can also use this to calculate the probability that we'll find it in the first place or the probability that we'll find it in the first 10, but the software doesn't give us the equation to this curve. It does a lot of the work for us. And what it's going to do is it's going to calculate a non-match probability for outliers in the sample distribution we're looking at. If we look at this a little more closely, as we said, we have the peak on the left, which is our non-matched peak on the histogram. And then we have outliers to the right, which are potential hits or possible matches to the sample under test. The software, looking at that curve, is going to calculate a confidence level, and it's going to be shown in a color distribution of where the sample outlier, or the outlier is with respect to our known non-matched distribution. Based on just the distribution of these similarity scores, we can make a determination of how likely each of these samples should be part of the known non-matched. Or another way to look at this is the likelihood that they are not a non-matched sample, which implies that they could be a match to the sample under test. Again, the software will not tell you it's a match, but it's showing you a confidence level that, hey, you should probably take a look at this and make a determination on it. What we really want to come out with, if possible, is that one outlier that says, hey, here's your likely match. And when we get these confidence intervals of non-match probability or rarity, we're going to find that when we see the ranked outcome of these searches using the software, we're going to end up, if there is a significant confidence, that the highest sample or samples will be flagged with a color. And then in our list of results, those flags are going to come out and be shown in the similarity score again, just to say, hey, here's a sample that you're probably going to want to look at. And when you get one of these samples, you can load it into the software and then go and use the virtual comparison microscopy of the system to be able to virtually compare one sample to the other to make a determination of, is this sample a match, is it a non-match, or do I have insufficient information to come to a conclusion? So that's a quick summary on the similarity values, how they're generated and used in the Evofinder software. If you have any questions about this, please feel free to email me or contact me. Again, my name is Neil Schrody with Leeds Forensic Systems, and please join me next week on January 7th when we're going to be going over the virtual comparison microscopy aspect of the Evofinder software. Thank you for your time, and I hope you all have a good day.